terminal characteristics of separately excited DC generator. That is terminal characteristic. Sometimes it is called as output characteristic, but I prefer terminal characteristic. Türkçe'ye dış karakteristik diye geçmiş, onu da yazayım. Dış karakteristik. Terminal karakteristiği diyen nadir kitaplar da var. Dış karakteristik. It is most important characteristic, in fact, because we choose machines with respect to their performance. And terminal characteristic shows us performance of the machine. For example, if it is generator, you know, a generator generates electric power. It converts mechanical power into electric power by using magnetic fields. That is the output, electric power. Now, output characteristic. When someone say terminal or output characteristic, here is, let me show you the figure. Here is the dynamo. Here is the terminal voltage. On the terminal, generally we supply some electrical loads. Here are loads. Here would be load current. Okay. Here is, in case it is electromagnet, we must excite, we must produce some magnetic field to convert energy. And now, as you see, on the terminal, there is a power. Power is a product of voltage times current. Here it is DC. You observe terminal voltage across the terminals A and B. And then here's the load current. So terminal characteristic is the relation between terminal voltage versus load current. That is called as terminal characteristic. Now, as a first example, we study on separately excited DC machine. So here is a, let's say, separate exciter or power supply for the field circuitry. We have applied some field current. We have induced some electromotive force inside. And then here is the terminal voltage. That is the no load voltage. VTO. VTO, no load voltage, because here is no load first. And since it is separately excited machine, load current is equal to armature current in this case. So here you see armature current. And across the terminals in the beginning, you observe armature EMF, that's it, EA. And then here's the equation. Write Kirchhoff's voltage law around this loop. Induced EMF across the armature is equal to, here is armature resistance inside the system, armature current times RA plus terminal voltage. That is the Kirchhoff's voltage law around this loop. So, if you make any arrangement, VT is equal to armature EMF minus armature current times RA. Houston, you observe the parameters. VT, here it is, and armature current or load current. Those are identical in separately excited machine. Those are identical, as you see. The same current flows. So, you should draw armature terminal voltage with respect to armature current. Remember your high school math theory. Y is equal to minus mx plus a. Y is equal to mx plus a. But here's m is negative, you see. So that is a line equation. Here it is. Ladies and gentlemen, that is the theoretical drawing, theoretical output. The voltage drop here is simply current times array. In no load case, let's substitute 0 here. Terminal voltage will be equal to armature EMF. It starts from here, armature EMF under no load condition or an average excitation. First of all, in the experiment, you need a voltage here. Let's say it has started from rated voltage, let's say, or some voltage, it doesn't matter. But it is close to rated one. It must be close to rated one. Here it is rated voltage. To have rated output voltage, you should make some excitation. So here you have some excitation. Let's call IFO. IFO will induce EMF O. That is initial condition. Initial condition. Then I make no adjustment on field current. I kept field current constant. Kept constant at its original starting initial value. We kept it at its initial value. And then we observe terminal voltage by changing load current, and it is equal to armature current here in this case. To change load current, we need adjustable load. We change load rheostat, so we adjust load current and armature current, and then terminal voltage changes, and you observe and record terminal voltages. You see that there is a smooth decrease in voltage. That is theoretical one. Theoretical. In reality, it is a little bit different. There is a nonlinear relation here. The reason why the voltage drops extra, the voltage drop here is armature current times array, you know, here it is. But these voltage drop cannot be seen in the equation. That is due to armature reaction. It cannot be modeled. We cannot make any certain equation for this. We can conduct some experiments machine to machine to determine how armature reaction causes some distortion, how it deteriorates the output. You need to make some experiment to define armature reaction effects. But you know that after this explanation, it looks like this theoretically, but in reality, here's a nonlinear change due to armature reaction. Magnetic field causes some drop due to armature reaction. That is the terminal characteristic for separately excited DC generator. Terminal characteristic. Do not forget. Ask yourself, what is the output? The answer is, this is generator, electric power is the output. What are the multipliers of the output? Electric power is a product of terminal voltage times line current. So multipliers are terminal voltage and line current. That is across parameter, uç değişken, across parameter. That is flow parameter, iç değişken, akan şey. Flow parameter. Terminal characteristic is the relation output across parameter versus output flow parameter. If you draw this relation, you will have terminal characteristic of any machine. It doesn't matter. For example, let me show you. In motor, let's ask ourselves, what is the terminal characteristic of motor? What is the output of motor? Output is mechanical power. What are the multipliers of the output? Mechanical power is equal to torque times angular speed. So that is across parameter, that is flow parameter. So the relation between across parameter versus flow parameter called as terminal characteristic of motor. The relation across parameter versus flow parameter in any machine defines terminal characteristics.